welcome back. We're going to do another example of a linear transformation. So in this example, we're looking at the vector space of all infinite sequences of real numbers. And the function t from the vector space to itself is defined to be t of the sequence x0, x1, x2, etc. is just going to be the sequence x1, x2, x3, etc. So basically, all we're doing is we're dropping the first term of the sequence and getting a new sequence. So first we're going to prove that this is a linear transformation on that vector space. So we have to first prove that this transformation preserves vector addition. And vector addition on this vector space is just where you add corresponding terms in the sequence. So you can think of the sequence as an n-tuple, but it just goes on forever. So an infinite sequence is similar to an n-tuple. So we're just going to add corresponding terms in the sequence to add the sequences. So let's look at t of the sum of A0, A1, A2, etc., and B0, B1, B2, etc. So we're adding together those two sequences. So first let's add the sequences. So we add term by term. We get A0 plus B0, A1 plus B1, A2 plus B2, etc. And now we're going to perform the transformation. And the transformation says just drop the first term. So t of this sequence is just going to be A1 plus B1, A2 plus B2, A3 plus B3, etc. All right, so now we can take this sequence and break it up into the sum of two sequences. So we can call it A1, A2, A3, dot, 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 plus the sequence B1, B2, B3, dot, dot, dot. And now we recognize these two sequences as the images of A0, A1, A2, dot, 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 and B0, B1, B2, dot, dot, dot. So we have just shown that t of a sum of two sequences is the sum of the images of those two sequences. So it preserves addition. All right, so now we're going to do the same thing with scalar multiplication. So scalar multiplication of an infinite sequence is just like scalar multiplication of an n-tuple in Rn. You just multiply each component or each term in the sequence by that scalar. So let's look at t of a scalar multiple of a sequence, A0, A1, A2, etc. That's going to be t of c times A0, c times A1, c times A2, dot, dot, dot. And now we're going to perform the transformation. So t just says drop the initial term. So now the image is going to be c times A1, c times A2, c times A3, dot, dot, dot. And now we can use the property of scalar multiplication of sequences. We can pull the scalar out and call that c times the sequence A1, A2, A3, dot, dot, dot. And now that sequence, it starts at A1. That's just the t acting on the original sequence that had an A0 term. So we just dropped the initial term. So we can call that c times t of A0, A1, A2, etc. All right, so we've just shown that t preserves scalar multiplication as well. So now that's the proof that t is a linear transformation. Part B of this example says find the range of this linear transformation. So the range, remember, is all the sequences in the vector space that are images of another sequence under this transformation. So let's take an arbitrary sequence in the vector space. This sequence is clearly the image of a sequence, any sequence that has some real number in the first term, and then the second term is b0, third term is b1, etc. I just chose 0 for the initial term. I could have chosen any real number, but I chose a specific real number to show that this arbitrary vector in V is the image of at least one other vector in V. So it has to be in the range. It got hit by at least one other vector. In fact, I could have put any real number in that first term. So infinitely many sequences get mapped to this one. So B is definitely in the image of the transformation. B was an arbitrary infinite sequence in this vector space. So any infinite sequence in this vector space is in the image. So that means that the range of T is the entire vector space. So the range of T is all of B. All right. Part C says, find the pre-image of the sequence 1, 2, 3, 4, 5, 6, ... All we need to do is, we need to find all the sequences that get sent to this one under this linear transformation. Not just one, but all of them. So notice that this sequence is the image of any sequence that has a real number in the first term, and then 1, 2, 3, etc. as the rest of the sequence. So it's sort of similar to part B, but we have to note that this first term can be any real number. So there are infinitely many sequences that get mapped to this sequence, 1, 2, 3, 4, ... So x0 is any real number. So this means that the pre-image of the sequence 1, 2, 3, ... is the set of all sequences of this form, x0, 1, 2, 3, etc., such that x0 is any real number. Okay, so it's a huge set of sequences. One sequence for any real number. All right, and now the last part of this example says, find the pre-image of the 0 vector in V under the transformation T. So it's similar to part C, but we're not finding the pre-image of the sequence 1, 2, 3. We're finding the pre-image of the sequence 0, 0, 0, ... So that's the 0 vector in this vector space. So what are all the sequences that get sent to the 0 vector, or the additive identity? Well, it's all the sequences that start with some real number, but then have zeros in the rest of the terms. The 0 vector, or the additive identity element, or the infinite sequence of zeros, is the image of any other sequence that has any real number in the first term and then zeros in the rest of the terms. So that means the pre-image of the 0 vector in V consists of the set of all sequences of that form, x0, 0, 0, 0, ... such that x0 is any real number. So it's similar to the pre-image of the other sequence in part C. But the pre-image of the 0 vector in a vector space under a linear transformation has a special name So the set of all vectors in V that get sent to the zero vector in W, in some other vector space, under a linear transformation, that set is called the kernel of the transformation. This set in part D here is called the kernel of T. And it turns out, and we will see this in the next section, that the kernel of a linear transformation is a subspace of the domain of the linear transformation. So in this example, the kernel of T is a subspace of the vector space of all infinite sequences of real numbers. However, in part C, we found the preimage of some non-zero vector in V, and that's not a subspace of the domain. So only the preimage of the zero vector turns out to be a subspace, and we'll see a proof of that later. All right, that's it for this example, and I'll see you in some other video.